My name is Gunnar Carlsson, so I'm going to be talking today about new ways of analyzing data and using it for artificial intelligence. By way of background, I've been a mathematician for all my career. In about the last 10 or 15 years, I decided and started to work on areas of mathematics, part of topology, the so-called study of shape, that we found very useful in analyzing large and complex data sets. So I'm going to present that for you. Over time, we have worked with the National Science Foundation and DARPA and have spun out a company on top of that, which is called IASD. So let me go ahead and start the presentation. So as you see, the title is a Data Modeling for Artificial Intelligence. I'm going to talk first in some generality about what's going on with AI and our point of view on that. And then over time, I'll kind of get into more of the guts and the detail. So what about artificial intelligence? What do most people think about, particularly if you think about where artificial intelligence was 20, 30, maybe even 50 years ago, it existed then. What most people think about is the process of performing tasks that people already do. So, and replacing people in that for various reasons. People maybe do them, but they don't do them as well or as accurately as we'd like. Maybe the tasks are too onerous. Various reasons why we want to do that, but it is a situation where there already is a human template for how the task is carried out. So think here about driving cars, personal assistants, recognizing images, and so forth. Again, the idea is to replace, in some cases, very simple cognitive tasks that people are already doing, and doing so with machines in an effective way. And that's a lot of what's been doing. I would refer to that as what might be called narrow AI. And I think where we're headed now is we're headed to problems that humans can't really deal with effectively. Situations where the scale of the problem is too large, the complexity of the problem is too great, that humans don't really deal with them very well. So this is the new stage of AI, what I would call broader AI. And so think here about fraud, think about cybersecurity, think about genomics, where one is dealing with long sequences of letters in an alphabet, large databases of such. So those are all situations where people really don't do those problems very effectively by themselves. So the question is, for this kind of situation, what are the requirements? What is it that is needed about a methodology for dealing with this with these problems? So I would want to argue that there are at least several requirements here, at least 5 of them. So the first one on the left there is what I would call discover. What that refers to is a good methodology for unsupervised analysis of data, to allow you to discover things about your data without having to already guess what's in it, make a guess, and then verify it. And it's very important to do this because I think humans almost always come with preconceived notions about how a problem should be solved. And here in this situation where there is no human template, there is no way in which humans have been solving the problem very effectively beforehand, one needs to discover that with an open mind, and that one needs a methodology that supports that. And so that, in fact, is going to be the main thing I'm going to be talking about later on the technical side. Next, one certainly also needs methods for prediction, for classification, for ways of understanding what happens as a new point comes into your data. What can you say about it? What information can you get about that point? And you want to do that in as flexible as possible a way. I think if we think about prediction, for example, we often think about regression models, linear regression models, which are kind of algebraic at their core. And those often work reasonably well. I think over time, though, what we find is that much of data, many of these tasks are more complex than can really be dealt with effectively, or at least in an ideal way by algebraic methods, and one needs to develop more flexible methods that recognize possible sources of systematic error. The middle one now, the one labeled justify, this was the one that was the most surprising to me as I became aware of it as we were developing the company here. And it came up for us in the context of financial regulation. We were working with a bank that had failed the stress testing CCAR process 2 years in a row, and they had failed for the following reason. They had produced some machine learning models, some rather complicated machine learning models, which had some predictive value, but nevertheless, the regulators looked at them and said, I don't understand these models. This machine learning stuff is a black box to me. I don't understand it, and so I can't put my faith in it. And so then it became very clear that what was needed here was a way of building models, machine learning models, that were not black box. We did not have that property. And so the idea is that one want to produce models that have a small number of features, and each of those features is explainable in the sense that it can be characterized in human terms and understood by someone like a regulator. Now, this whole notion permeates the subject, in my view. I mean, it just surfaced for us with the financial regulators, but in fact, we see it in the healthcare side for sure, where one is dealing with MDs and other people working in healthcare. But actually, it's a big theme. I think one is finding that really the idea that one should have a black box that doesn't need justification or explanation is not really viable. And just to add a little more to that, we kind of need to not only justify the answers that we get, but we need to understand how the methodology works underneath. So, think about a car, for example. The idea of it's easy to determine that the car is not working. Okay? But what you, of course, need to do is, in addition, you need to understand why it's not working, and you need to understand how to fix it. And that is something that one needs to have, in my view, in all of these artificial intelligence algorithms and methodologies. Then finally, you need to act. You need to be able to recommend actions or even perform actions in some cases based on the justifications and the predictions, and ultimately also learn. You need to be able to modify the model that you have based on new data coming in. And that new data may come directly from the outside world, but it should also include data about the human interaction with the software or with your method. So in other words, the effect that you're imposing or using this artificial intelligence methodology within someone's system, that in fact will have feedback effects on it. We'll even see one of those. And so one needs to be able to learn on that basis and modify the model based both on strict outside data and also data coming from interactions with the models. Okay. So let's think about what are some data analytic requirements here. We need methods for unsupervised discovery, where there are no human templates available. Methods need to be able to give answers with justifications, and they need to be understandable. And it's also important to have diagnosis of failures. And so diagnosis here means detecting the failures and then also determining the reason for them and how to adjust. Okay, so now let's talk a little bit about what the current situation here is and why there's a need for a new method for data analysis. So in a certain sense, too many possibilities guarantee failure. And think here about the fact that the data that we see is growing, not just from the point of view of the data sets, the number of sets of rows, but also the set of features that we collect. Instead of collecting 3 or 4 or 5 features, we're collecting tens of thousands or even millions of features in many situations. Now, what that means is that the set of possible hypotheses, which are the things that the guesses that you make about your data, they grow very rapidly because they grow as collections of features do, and that's an exponential growth. So in some way, this hypotheses are growing extremely rapidly with time, to the point where it's becoming harder and harder to think through all the possibilities and make educated guesses. And so here then is the what we can think of as the current pipeline. We have some very smart people on the far left. They are making some hypotheses. They have some thoughts, some theory that they have developed about the data. One then has to validate those assumptions and then use machine learning and data science to determine whether or not the hypotheses are correct. If they are correct, you get an insight, and then you would go through the validation process and ultimately deploy. Now, there's also feedback here. In other words, in many cases, those hypotheses will not be accurate. And in that case, that information gets fed back to the analysts who might then modify their hypothesis. But the problem with this is the one that I mentioned in that curve before, which is that, in fact, the number of hypotheses is growing so rapidly that this method over time will really break. So it's people intensive. There, you can only generate a very limited set of hypotheses here, sometimes limited insight from the machine learning, and often is very time consuming. So what I want to show you instead now is the approach that I want to discuss, which is this. It says, let's take the data and let's not just use it to verify hypotheses. Let's move it to the very front of the stack, and let's go ahead and construct something about the data right away before making any guesses about it, making any thoughts about it. And then let's have the analysts look at it. And they're going to look at this kind of model that comes out here that allows them to make much more educated and better, likely to be correct hypotheses about the data. So we'll have more insight about the data to start with. Ultimately, then we'll do model identification. We'll certainly have to work and confirm the models. We'll get insights, but we will get them much more rapidly and easily. And also, there'll be a lot of possibilities for feedback back to the models here. The models are, very good, have the capability for learning. Okay. So, all right. So at this point, this kind of describes the problem and in very rough, high-level terms, what a solution might be. So what I want to talk about now is to get into the weeds a little bit, not the weeds so much perhaps, but dig in a little deeper into what the methodology is. Okay, so as a first statement, though, we want to argue that the notion of the big data, which has been kind of synonymous with with large-scale data analysis, the big problem is not really the big in the data. It's not the data size, but it's really the data complexity. And the complexity here comes in many different forms. One is the input complexity. So you might consider, the databases that consist of genomes, for example, or images, free text, databases of molecules, where you have, systems that are given to you by positions of atoms and bond lengths. Very hard to feed those into a simpler model, which would be more like a spreadsheet. I would say that the simple models, from that point of view, are spreadsheet. With numerical entries. But even within the context of spreadsheets, where you do have simple input type structure, you nevertheless often have structural complexity, which is something that we'll talk about. It requires an organizing principle, and our organizing principle is the shape of the data. Okay, so now just to sort of put this in context, there's the whole notion of exploratory data analysis, which was really introduced by John Tukey a number of years ago. He wrote a long book on the subject, and what it said was effectively, we need to be able to look at data in many different ways. We can pass along information in many different ways. It doesn't all need to be in terms of just the numerics of a spreadsheet. It can be produced visually in many ways here, and that's what these pictures show. But he kind of argued for that we should be able to do a lot of exploration. We should be able to produce richer models that indicate more things than just simply the usual algebraic models that we have. And it's sort of summarized in a quote, though. The rationale behind this was this quote from from Tukey, which says that it's much better to approximately answer the right question than to get some very exact answer to the wrong question. That, the idea that one gets some very approximate, some kind of understanding is very important, and the degree to which one then makes that more and more exact is of course important, but the primary thing is this approximate answer to the right question. Okay, so now what I'm going to be talking about here fits into this context very nicely. This should be viewed as a part of exploratory data analysis. So let's talk about the shape of data, for example. I suspect everyone who is listening here has looked at data that looks like this. And you can see here, there's a straight line will make a natural fit on this. So what is that? That is replacing the data set by a shape. So that's very powerful when it can be carried out. It allows you to predict values. It gives you a great deal of understanding in terms of what variables vary in what way with other variables and so on. There's a lot of information in such a model when it exists and it is appropriate. However, oftentimes the data might look like this instead. And now you see here, there's no straight line that fits this. However, there is a natural structure, something that jumps out at us in a very straightforward fashion, which is that it breaks into three groups. So here, that could be also viewed as replacing the data by a shape. In this case, the shape, though, is something we might not even have thought of as a shape. It consists of three discrete points. Would approximate this. A lot of math around both these things. The math is basically, it doesn't overlap. And so we've developed two methodologies here. And now we might hope that we had covered everything with these two situations, but in fact we have not, because we might have data that looks like this instead, that is loopy. Oftentimes this comes out when we're dealing with time series, we're dealing with periodic or recurrent behavior. We'll see this. Now, at this point, we could say, okay, we'll build a loop detector, and then we'll have those three cases covered. Maybe that'll do it all. We don't really believe that. We don't really have confidence in that. And then, of course, when a data set like this one comes along, the one there you can see with the three flares coming out, this might happen when you have data which has a normal mode of behavior, like in an airplane flying at altitude in non-turbulent conditions, and then three extremal modes, which might be takeoff, landing, and flying in turbulent conditions at altitude. So at this point, we're convinced that we don't have, we should not attempt to sort of go shape by shape and build methodologies for each one. It's extremely costly in terms of time, and we really need a modeling mechanism that instead is able to model all these four and many others, in fact, all possible shapes in one package. And that package exists, so let me talk to you about something from the mathematics side here. This is the development of the subject of topology, the study of shape, actually began in the 1700s, 1736 to be precise. And it was a mathematician, Leonhard Euler, and the Swiss mathematician working in the Russian court, who was asked to solve a recreational math problem, namely, can I cross all the 7 bridges going across the river Pregel in Königsberg without crossing any bridge twice? And there's a lot of irrelevant data in there. The data consists of, for example, the depth of the river, the size of the islands, the length of the bridges. All of those are irrelevant, and all that's irrelevant is the simplified model on the left, which has 4 nodes, and it's a network model. You can see 2 of the nodes in the middle there correspond to the 2 islands. The other 2 correspond to the riverbanks, and the edges correspond to bridges. And from this model, he was able to quickly reason about the data and get to the answer, which is that you can't do it. So question is now, how do we do this? And I won't go into the full details, but I'll just sort of show you rapidly. One begins with a projection. One can actually have 1 or more projections. They usually are not coordinate functions. They are statistical measures like density or like centrality. They might also be linear or machine learning models like PCA or multi-dimensional scaling. But what we'll then do is we'll bin the data based on this projection. So we'll divide it up into various intervals. You can see here we bin the data in a repetitive fashion or redundant fashion, in that some of the bins, some of the points are contained in more than one bin. So you can look at the top there and see that some of those orange points are contained in both bins. What we'll then do is perform a clustering step on each of the bins, never the whole data, but on the bins, and create a node in the network for each of those clusters. So when we do that, now we've created a bunch of clusters, and this is for you who know this terminology, this is soft clustering. The clusters can overlap. And then now, but we don't just have a set of clusters, we're now going to connect any two clusters that overlap by edges like that and create this network. So this is quite, you can see we've in fact recovered the structure of the data set, which was a loop. We've lost some detail concerning the curvature and so on, but that's really, we're often, in fact, we usually are willing to sacrifice a lot of detail to get some high level understanding. So the input needed is listed here. We need a similarity measure on the data, and that is really the main thing, and then a choice of these projections. Various notions available in company software. We produce a lot of options, but you can build your own. What I want to show you now is a few examples of how this kind of analysis is relevant. So our company has a number of collaborators, academic collaborators mostly. And in this case, this comes from the Mount Sinai group, or a group at Mount Sinai Medical School in New York, studying type 2 diabetes. It's a complex data set. It's about 11,000 patients. It contains both medical record data as well as genomic data. And what you see here in the model is that it really has a very striking structure. It has 3 groups. They're connected by thin wires, relatively thin wires. And the conclusion that the investigators were able to draw here is that what we have thought of as a single disease, which is type 2 diabetes, is in fact 3 diseases, and actually they've moved beyond that to 4 diseases now. And the key thing here, the interesting thing is that they really are different. So the one is what we think of the standard notion of diabetes with obesity and kidney involvement and so forth. But a second one is very strongly related to cancer. And a third one is then related to so-called neuropathy, neurological symptom. So, of course, this is critical to the notion of precision medicine, which is a huge trend in the medical world at this point. And so, to know that actually we're dealing with the 3 or even 4 diseases means that we can develop different treatment regimes. And dealing with drugs, for example, it makes the drug discovery process much more likely to succeed, because you're already dealing with the smaller subpopulations than you are if you dealt with the entirety of all the type 2 diabetics. Another aspect of precision medicine is illustrated by this one. So this is another group working at Stanford, the David Schneider group. He's studying the behavior of progression of infectious disease. So here, he's taking genomic measurements and also physiological measurements. And think about what should happen with a disease. You start out in a healthy state, and you then move along the trajectory as you're getting sicker and sicker in the data, until at a certain point the immune system kicks in, and now you start to move along a trajectory and ultimately get back to the healthy state. However, that trajectory is not the same as the one that we had as we were getting sicker. It involves a lot of immune system activity. And so here the idea is that we've built a precision model for the state rather than the time. So where you are in these loopy models, as you can see here, it determines the state you are. It's correlated to a certain extent with the time of the infection, but in fact people and subjects in general move through these phases at different rates. Not only that, when we're dealing with a person or dealing with someone presenting with with a problem, then we don't always have access to when they were infected. In fact, we generally don't. We don't have access to that time anyway. And so it's important to have these kind of time invariant state models. Okay. Another one here. Let's see. This is an analysis that was done that we did actually in the early days about breast cancer here. The finding here was that there's a group in the lower right there that consists of about 10% of the patients in the study, 8% actually, but where the survival is perfect. The model was constructed without using any survival or clinical information. It was entirely using so-called microarray analysis. What's interesting, though, is that the technologies for doing the microarray analysis are there are many different such technologies, and they're completely incompatible, so they don't have the same coordinates. But what you can see here is that these are, if you look at the upper two boxes here, were based on one data set. In fact, the one from the preceding study. And then the other one was a completely different technology. But what you'll notice here is that the models are quite similar. So that solid structure that you see there, that solid with a slight Y look to it, that is the survivors. And so that's the same in both of them. And then you can see that the non-survivors break up into a number of small groups. Even those groups correspond to each other, which gives you confidence that you're seeing the structure of breast cancer itself as opposed to how it's seen by one technology or another. Okay, let me see here. I think we are getting close to the end. The description here of the value of the technique as related to ordinary clustering is kind of illustrated here. The group, that high survival group, which is one of the flares coming out on the lower right there, you'll notice that in the standard model, which is a dendrogram, it breaks up into many different pieces here. One would not have been able to identify that group with much precision using the hierarchical clustering. And so that is a critical problem there. Okay. Now, so let me talk about how does one typically work with a model like this. So this is a network that is built off cases for in healthcare where one has some ground truth about fraud. Now, but on the other hand, you don't want to believe that the ground truth that you have about fraud is the whole story. You want to be able to capture the possibility that someone might not might be doing something that is entirely new. And that would be incorporated in the outliers here. So the outliers are certainly something that I would want to look at. They would want to constitute some kind of anomaly detection. On the other hand, I also want to understand the things that I already know about. I want to understand if someone is doing something kind of standard, I want to understand that as well. And so I can take the network and I can color it by presence of fraud. And so in this case, that's indicated by red here. And so one has several groups here that are actually, these are descriptions of things. These are samples of people who actually came with fraud. Okay. So we want to find the insights in the network so that the fraud is localized in special areas. Right. And now one also wants to find explanations for it. And so here are the explanations for that particular group in the upper left here. So in this case, they were coming from a particular country that was of a lot of importance. Okay, and so then one can detect these groups and actually build models on them. Let me conclude by talking about a work that was done with Lockheed Corporation. So this is a company in which they are very interested in studying their programs, of which they have thousands going on with the federal government at any one time. They would like to be able to predict which ones of those are going to downgrade, which ones are going to go off the rails. And so this is, again, the data is fairly complex. The data consists both of structured data in terms of the timelines and all the particulars about the contracting and the projects and so on, but also free text from the communications of people and reports and so on within the program. And so building off that data using some very simple natural language processing, one can be able to predict with much greater accuracy than they had been able to at an earlier stage the likelihood that a project was going to downgrade. So these are just a few examples. Let me just try to end the discussion here by saying that we're not talking just about visualization here. It looks the pictures are pretty, but in fact, what you can do is you can interact with these models in many different ways. You can select groups in the way that one would with Photoshop or Illustrator. One can then work on those groups, find the explanatory variables. One can color by quantities of interest. One can even take models that you have, existing models, locate areas of systematic failure and modify the models, perhaps by introducing features. There's a whole array of things that one can do. I should also say the ability to study the space of features. So when you have a data set that is a spreadsheet, you can study the space of columns just like you can the space of rows. And to find the geometry on that is extremely instructive and can sort of address even questions in confirmatory data analysis as well as exploratory data analysis. So it is a full-blown modeling framework, not just a visualization thing, and that is kind of how we use it. We found it to be very effective in dealing with very large and complex data sets. So at this point, I'm going to end the presentation, and let's see where we are here. Okay, let's see. So I see a lot of highs from China. Hello to everyone. Yes, very good. Hello from Singapore, from Aachen. Yeah, talk a bit more about how the projections work. Yes, I can absolutely do that. So the projections, so again, it looked like it was a projection on a coordinate, and one could do that. That's we call that a data lens. But in fact, what we want to do is we want to use many more different things. So particularly statistically meaningful things that are about the geometry of the data. So for example, the idea of using density is really vitally important. It allows you to separate things that are systematic from non-systematic, things that are anomalies from that are not anomalies, and so forth. One might also use centrality, which has some of the same properties as well. But then one can use machine learning things, multidimensional scaling, and principal component analysis. All those things are quite useful and interesting. Let's see, how do you find a good distance measure? Let's see, so, this becomes an art form a little bit. What's quite interesting, so first of all, we know that for certain kinds of data sets, it's really, very sort of the correct thing to do to use some particular ways of measuring the distance. So, for example, Euclidean distance is fine. Typically, one wants to normalize by the dynamic range of the variables into something called variance normalized Euclidean. But there's also Hamming and so on. It really depends on the subject matter that you're dealing with, and oftentimes it's an art form in constructing one. So if you have some very complex data that involves, say for example, visits to an Amazon web page, then you probably have to design something that you believe captures the notion of similarity. Yeah, so the question is, can I relate or compare the algebraic topology approach versus methods like PCA or some other unsupervised methods? Yeah. So first of all, the answer is that the topological methods, in my view, are simply a next stage. I don't want to they're not sort of separate or distinct from the PCA or other methods. They are refinements of it. So, for example, as I mentioned, we might use as part of our projections a PCA, or an MDS, both of which are unsupervised methods. What we find is that we get much better resolution, and we have papers that demonstrate that there are things that are missing if you take just the PCA1 or PCA1 and 2 and so on, and kind of look at that. You're going to miss stuff, and that you can capture it kind of nicely by saying, let's use this methodology that I just showed, but now we're going to cluster somehow all the points that have a fixed PCA1 and PCA2, and that turns out to do some very nice things. Secondly, what I would regard the topology method as a very useful combination of continuous and discrete methods. So PCA could be viewed as a continuous method, and clustering is a discrete method. The combination here, and particular getting an output that retains some of the geometry. The output is not just a scatter plot. The output is not just a clustering or a partition. One finds this representation of the distance or of the similarity map is extremely quite useful. Which tool can be much better used today to learn Python? Yeah, well, look, of course we use Python a lot. Well, I should say the software that we have, which uses this, which creates these topological models, in fact, has a Python SDK in it, so a software developer's kit, and also a prototyping environment called Envision. So all these things, both R and Python are things that are extremely useful in creating input to this method. They can, of course, be used in a standalone fashion, but this topological method on top, built on top of those things, produces, much more. It gives you much more kind of resolution on the data. It gives you the ability to find the insights much more rapidly using these notions of coloring, what I would call hotspot analysis, which is finding hotspots for concentration of fraud and so forth. How computationally intensive is the topological method? Yeah, well, it depends on your range, but the reality is that the method, because it's so simple, and in particular it's embarrassingly parallelizable, means that over time it's going to be less computationally intensive as the scale of the data grows very rapidly. Of course, there are issues. We are handling those at the company and kind of constantly improving what we do on scale. We're not finding that scale is any kind of obstacle to us in what we do. That's just not the main problem. Oh, great. Yes, multiple similarity measures to create multiple resulting networks. That's a great question. We absolutely do that. And the point is this, that in complicated situations, we may not know what the right similarity measure is. We may have several that we have in mind. And the thing is that you want to be able to compare those. And so here's what you can do, and actually this is supported in the software. What you can do is you can build the network models for both. Or say, an array of networks, and put them on the screen at the same time, and then select a region in the one network, and it will light up the other, where the corresponding points are in the other network. Gives you a lot of insight into what's being done, what these networks are doing, and what the effect of the similarity measures is. So it becomes a very nice tool for working with and understanding the different measures, the different similarity measures, and working with them. I want to add one other thing, though, also, just for, which is that what we've done, which I'm really pleased about, is to use combination of so-called persistent homology to identify what are the interesting networks. You see, there are many choices here. The networks can be built at different levels of resolution depending on how many bins I choose, but there's other parameters that go in as well. We have a primitive way of sort of automating the selection of those things, but it's very primitive. It gives reasonable answers at times. What we've done now is to say we want to actually study the whole the structure of the networks and find the interesting ones. And so what we've done is build persistent homology signatures, which it turns out fit beautifully into convolutional neural nets. And so we've been able to now use that to have the machine learn what's an interesting network. And so that is going to greatly improve the discovery process. How does this help in financial services? Well, that's a big area for us. We're working with one of the largest banks in the world, HSBC, in several areas, and not just the HSBC, but other banks as well. So anti-money laundering is something where we've had a great deal of success. I think you'll find that on the web. But in addition, we can do a model improvement where you have a model, say a linear regression model, but you build the topological model, and you see that although that model is very good in the aggregate, there will be some areas of systematic error, and we can then help you to correct those. It also, using this feature space analysis that I described, it can allow you to build simplified and very understandable models. My view is that this whole methodology is a way into the problem of making machine learning into a not a black box thing. I think that it's exactly the right mix of stuff here to be able to really carry that out. Yeah. So any references? Yeah. Let me type one in here. I'm typing in the title of a survey paper, and this is in the bulletin of the AMS. 2009. So that's my survey paper. I also have a book called, with my colleague, Francis Campion, called Machine Intelligence for Healthcare. So also a book. Healthcare, and it's available on Amazon. Yeah, so anyway, those two things, but actually there's a lot. If you look up now computational topology and topological data analysis, it's a really thriving area on the academic side, and so I kind of recommend you to look for it. Anyway, listen, thank you all for your attention this morning. Great questions, and so I enjoyed presenting this. Yeah, right, the fires. I guess it's down here. I can still, I see in the air here, even though we're about 70 miles away, the air quality here is much worse than it normally is. So even at this point, we're seeing effects. Unfortunately, also have friends who have had their houses burned down. So but definitely staying safe. All right, thank you all.